Okay, this was a question that me and my friends were really struggling with, and the teacher also got it wrong. Okay, this question gives us, oh, let me label the arrows. Give me a sec. There we go. This question shows us a heat engine, basically, and it tells us to calculate the efficiency. Now, let's recall that efficiency is net work done over Q in. So heat transfer in, which means heat transfer towards the heat engine, which I'm just gonna write as this for simplicity's sake. So when we're calculating net work, it's really simple. We just calculate the area of whatever's enclosed by the curves. Oops. Which in this case would be 8, because there's 8 squares within this curve, enclosed curve. Now, what's really tricky is finding heat transfer in Q in. It's quite tricky, but I have a strategy for it. First, I'm going to choose I'm going to find which leg absorbs heat. So there's 4 legs that encloses this curve. There's 4 legs in total that makes up this curve. And I'm just going to find the leg that absorbs heat, so where Q is positive. Oops. Okay, let's first do that. I'm just gonna label this. Let's look A to B. Will it absorb heat? No, let's see. This is the second law of thermodynamics. Heat transfer is change in internal energy plus work done. You can tell that there is no work done for A to B because there's no area under the curve. But we can tell that there is an increase in internal energy because, recalling this formula, the ideal gas formula, PV and R is T. And for A to B, volume remains the same, everything else remains the same except for P, and P increases, which means that T also has to increase. So although work done is 0, change in internal energy is positive, meaning that Q is positive. So yes, heat is absorbed. Now, let's look at B to C. Q is change in internal energy plus work done. We can tell that there is work done, and it is positive work done. Right over here. How do you know it's positive? Because the arrow is pointing this way, which suggests an expansion. Remember, for a gas to expand, it has to do work. So, work done is positive. Now, what about change in internal energy? Again, let's use this formula here. Only difference is that now both the pressure and the volume has increased, which means temperature obviously increases. And because internal energy is proportional to temperature, internal energy is also greater than 0, which means Q is greater than 0. So yes, heat is absorbed. Now you get the gist of it, and you can find if heat is absorbed or released for C to D and D to A. And I think that's quite simple to do, and with what I've explained so far, I can quite easily do it. So I'm just going to skip over and just tell you that C to D and D to A, there is energy transfer from the heat engine to the surroundings. So heat transfer is negative, not positive. So when we're calculating Q in, we are only going to look at A to B and B to C. Alright, now we just have to find the numbers. Let's first calculate. Let's calculate total heat transfer for A to B. I'm first gonna say that, again, there's no work done for A to B, so we just have to find the change in internal energy. Now, there's a formula on your formula sheet that can help you, which is change in internal energy equals 3/2 nR change in temperature. Oh, but we're not given temperature here, so what do? It's fine, we can manipulate it. And how I'm going to manipulate it is by saying that change in temperature, delta T, is equal to temperature B minus temperature A, which is right. And I can simplify that into actually, I'm just going to write it as that. Now, does this look familiar? Let's recall PV is nRT. My gosh. So, you can simplify this back into and we can just find these values on the graph. You guys can do it yourselves. I'm just gonna find it real quick. 6 minus 2, which means 6. So the heat transfer at A to B is 6 arbitrary units. Now for B to C, change in transfer in heat is change in internal energy plus work done. And we can use this same approach, the same formula, to find change in internal energy for B to C. So change in internal energy is PCVC minus PBVB, which is 18 minus 6. So 1.5 times 12 is 18. Now let's find work done. That's pretty simple. We can just use P delta V. Now that would be 3 times change in V is 6 minus 2. So 6 minus 2. Oh, sorry. Equals 3 times 4 equals 12. So heat transfer is 12 plus 18, which is 30. But we have to find the total Qn, which is 30 plus 6, which is 36. And again, efficiency is net work done divided by net Qn, so 36. And work done, we calculated it already. 8 is 2/9. And that's the answer. Let me see if I got it right. Oh, yeah, I remember I did get it right. Yep, so there's the answer.